It's our pleasure that I welcome you to the sixth day of this ATAL FDP. So we want to welcome you here and hope you will enjoy this session. Our I would like to tell you that our speaker for today's session is Professor Arvind Kumar Lal from Thapar University. Now I introduce our speaker, that is Dr. Arvind Kumar Lal, is currently working is a professor in Department of Mathematics from Thapar University, Patiala. His research interests are astrophysics and reliability. Professor Arvind Lal had PhD from IIT Roorkee. He received Khosla Research Award of University of Roorkee in 1991. Professor Arvind Lal has performed a number of administrative responsibilities. He has delivered many invited talks. He has also received 6 sponsored research projects. Professor Arvind Lal had supervised 10 PhD students and one is going on. He supervised a number of MPhil and MSc students. He is also the author of 2 books. Professor Lal has organized many short-term courses and conferences. He is also the reviewer of many journals. Dr. Lal has published a number of research papers in SCI and Scopus journals and conference proceedings also. He has Google H factor is 16 and Google citations is 526. Scopus H factor is 8 and Scopus citation is 218. So now let's welcome Professor Arvind Lal, who will deliver a talk on equilibrium structures of differentially rotating stars. So now please come on the dais, sir.
Thank you so much. Thank you, Dr. Anju Saini, Dr. Seema Saini, esteemed members of the organizing committee, and my dear participants. Really, it is a matter of great pleasure that the Department of Mathematics, Graphic University is organizing 2 weeks online offline ATAL FDP programs. And the title of the program is Mathematical Modeling of Differentially Rotating Stars in Stellar Systems. This FDP has a theme which is very important and has astrophysical significance. It is not only an astrophysical significance, but has a wide application in interdisciplinary mathematics. So I hope this program will certainly be helpful to the researchers to present their present the latest development and innovation in the different types of mathematical modeling. So although it is a part of the related to the astrophysics, but it is a part of the applied mathematics. So I hope this program, this lecture will be beneficial because my topic I have chosen is the equilibrium structures of rotating stars. I have done my work in the same area and also supervise many students on the topics rotating and pulsating stars. This topic is very relevant to your theme of this program, that the equilibrium structures of rotating stars. It looks a little bit different from mathematics, but it is a part of applied mathematics. See, when you say equilibrium structures of rotating stars and then say stars, but we as a mathematician only discuss the stars in the theoretical ways in some different ways, because we don't have, we take some observational inputs, we have observational data to verify our model. So we try to develop some theoretical model of rotating stars, and then try to find how our theoretical model of a star is relevant to the realistic ones. So first of all, that in this case, we have used the words stars, then rotating, then equilibrium structures. So all the terms should be clear. Then we go further and then try to understand how a simple model of rotating stars can be constructed. So basically, a theoretical model of the star is essentially a self-gravitating gaseous sphere in hydrostatic equilibrium and thermal equilibrium. It is very simple. So a star consists of various gases. I will not go in the details of the structures, like particularly the birth of stars and the evolution of stars. I will not go for that one, but it consists of a spherical gaseous sphere. So you assume that it is hydrostatic and thermal equilibrium states. Therefore, theoretical studies of the equilibrium structures of gaseous spheres are often carried out to understand the nature of the inner structure of the stars, which are responsible for the various phenomena observed in the real stars. Right? Because our theoretical model of star is nothing, it is a gaseous sphere. And many equations related to the structures of the stars we perform on the spheres and then go further. So, whereas it is fact that some of the stars are observed as a single stars, and also some of the stars are observed as stars in the groups in 2 or 3 and many. That is, we say sometimes binary stars or multiple stars like this. You must be heard the name of single star. Our sun is a single star. Many other stars, Cygnus Alpha is many stars. So it is observational fact that stars are observed as a single as well as group stars in group. Stars in groups are called sometimes binary stars and one stars, and other stars are rotating, revolving about this first one, and many more, and multiple stars. It is also observed that some of the stars are rotating about their axis, just like our Earth is rotating about their axis, and Earth is also revolving about the Sun. So just like here, any star is also rotating about their axis, right? And when we rotate, a star is rotating about their axis. The rotation may be of different type. Sometimes the rotation is solid body rotation. That is uniform rotation. That is every fluid particle inside the stars having the uniform angular velocity. Each particle is rotating with a uniform angular velocity. So this is called solid body rotation. And some stars are rotating differentially. Differentially means a star consists of gaseous substances. So it is supposed to be fluid particles. So angular velocity of each fluid particle, each element is rotating with different angular velocity. Angular velocity varies point to point from the axis of rotation, and that's why we say a star is rotating differentially, not with solid body. And one of the interesting example of differentially rotating star is our sun. Our sun is rotating differentially. The angular velocity of near pole and near equator, they are very different, widely different. So therefore, this is not only sun, there are many stars which are rotating differentially and also rotating uniformly with solid body rotation. So we have this type of star also rotating with solid body as well as differentially, right? So we say that this star is rotating. Then if we assume that the equilibrium model of a single non-rotating star, suppose the gas star is nothing, it is a gaseous body. A single non-rotating star is supposed to be a gaseous sphere. Then the equilibrium structure of such a star must be distorted rotationally. So we can see such a gaseous sphere as a rotationally gaseous sphere, right? And similarly, if the equilibrium structure of a star appearing in the binary system. Binary system means having two components, just like Earth and Moon. This we have similar type of many stars in the space that is called binary stars, trinary stars, multiple stars. So in the binary star, the equivalent structure of such stars appearing in binary systems or multiple systems will be tidally distorted gaseous sphere if the star is not rotating, and rotationally and tidally distorted gas sphere if the star is rotating as well. I have used the word tidally distortion. Tidally means what? If one is a component, second is other component, both are the gas sphere. Due to gravitational attraction, gravitational pull, there is tides, and due to this tidal force, the structures will be disturbed. So we say it is tidally distorted. If the gaseous sphere is disturbed by the rotational force, it is a rotational distortion. So sometimes, if the star is rotating only, the gaseous sphere is tidally, rotationally distorted. If the stars in binary component is rotating as well as tidal force also, then we can say this is disturbed, affected by both rotational as well as tidal forces. So therefore, we have two different effects on the structures. One is the rotational effects on the structure, how rotation affects the gaseous sphere, which is assumed as which is in the form of stars, and also how tidal force disturb or affect the structure of the gaseous sphere, which is also the form of stars, right? And when both the components, rotation and tidal force, simultaneously work in the binary system, we say our structure is disturbed or affected by rotational as well as tidal forces. So in the present discussion, we confine our work to both rotational as well as tidal distortions on the structures only. Although we have confined our discussion to the structures only, but it is not the only part. We can also study effects of these two parameters, rotation and tidal forces, on the pulsation, oscillations of the stars. There is also oscillation of the stars, pulsation, because the brightness of the stars is varying time to time, and that's why there is oscillation. So I'm just leaving that part. So the same concept can also be applied to the pulsating stars also, right? So I have not touched that part, but it is also. So basically, our concept is how to analyze the effects of rotation as well as tidal forces on the equilibrium structures of the stars, right? So first of all, I have already discussed types of problems. Problem is I have taken the stars. Stars is rotating both types, maybe uniformly, maybe differentially, and also considered binary stars. Binary stars I will discuss in details later on, but it is nothing. Just like our Earth and Moon, we have one stars, a bigger stars, a larger stars, and any other stars in size, smaller in size, they're revolving about the prime larger stars. We see this sort of star is a binary star. I will discuss in details, right? So there is a there is a in-depth study to study the effects of rotation and tidal force on the equilibrium structures of gaseous spheres. And this study may be of some help naturally, because it is a part of this astrophysics stars. So naturally, this study may be helpful in better understanding the nature of the observed phenomena of rotating stars and stars in binary system and also multiple system. I'll come in the discussion to some of those problems, not all the problems, some of the limited problems. The problems of determining the equilibrium structures of distorted gas phases has been studied in literature details, but the effects of rotation and the effects of tidal distortion of stars has not been studied completely. Some of there are many works on this problem. Complete works means effects of rotation and tidal distortion of stars has been discussed by many authors, but they are not understood what is happening inside the stars, right? So therefore, we have here we have chosen this type of topics to choose to discuss in brief what are these problems, how we tackle these problems mathematically, right? So attempt has been made in the literature to determine these effects on the structures in our of the structure of the stars as well as the binary stars. But the theoretical model of the stars is considered as a gaseous spheres, so that this problem has been analyzed not completely in exact form. The problem has been analyzed in the approximate ways, right? And and therefore various authors worked on this problem. We can say the problem started from the work of our well-known professor and Nobel laureate Chandrasekhar. He started the work in 1933. He published series of papers on this work, right? Particularly he studied the problem of first order, and applied this problem to the rotational, tidal, as well as binary systems. Since then, several authors works on this problem. Gopal, who studied in 1970 the concepts of Rosset coordinates to study the problems of rotating stars and stars in binary system. Further, our well-known our professor Mohan and Saxena in 1983 used the concepts of Kipnahan and Thomas average approach in conjunction with the results of Gopal's of Rosset potential to determine the combined effects of rotation and tidal force on the structures of theoretical model of the stars. So we have this type of situation, we have our works, but we use the words Kipnahan Thomas averaging technique with Gopal's results, then we need to understand what is the Kipnahan and Thomas averaging technique, what is the Rosset potential through which we develop the model of rotating star, right? So next is here, I have just considered a simple examples of stars. Here, this is a picture you have seen. One is a circle here, and larger circle, which is inside this, we have written the words M0, and then here it is a smaller one. I have written M1 inside. Basically, it is nothing. It is a binary system of stars and rotating about their axis and revolving about their common center of mass. Basically, this is one of the mass known as a primary component of the whole system. Whole system is known as a binary system of stars. The pair of stars. One pair is this. This is called primary component of this binary, and this is smaller in size. It is called secondary component of the binary system or binary star. So this is a system. This is a complete binary system where one is primary, second one is a secondary stars component. So one component is primary, second component is secondary stars. So basically, primary, which is nothing, whose mass M0 is nothing. This M0 represents the mass of the primary component of the stars, and M1 represents the mass of the secondary component of the star. Generally, primary component is much larger than secondary component. That's why I represent is a larger circle and this smaller circle, and both M0 M1 are the masses of both primary and secondary components, right? Because of the rotation and tidal effects, because both are rotating, this star is rotating about their axis. This is also rotating about the axis. The whole system is revolving about this line in between this line. Here, this line is the center, passes through the center of gravity. It is common center of mass. The whole system is revolving about this common center of mass. So this is the system. So because of the rotation, and both this is the primary much larger than this one. So naturally there is a gravitational pull and there is a tidal force. Tidal force works in between these two. So that's why we consider both the things, rotation as well as tidal force influence the structures of the stars, right? So because of the rotation and tidal effects, of the companion of the components of the binary system, this system becomes rotationally and tidally distorted stars. Whole system becomes rotationally, and because there is rotation, both the components are rotating about their axis. This one, and whole thing is revolving about the common center of mass, as well as there is a tidal force between these two masses. So because of this, their compute is distorted by the two factors, rotation as well as tidal forces. So now we'll
Excuse me,
how
sir.
this. Yes,
Sir,
yes.
sir, your screen is not visible here.
My screen is not visible.
Yes, sir.
Right? Visible hai ma'am, visible. This time we can say this figure. This sir is discussing
It
this
is.
time is this figure only.
Am I audible? First of all, let me know. Am I audible?
Yes, sir, you are audible.
Yes,
And
sir.
your
Audible, sir.
My picture is not visible.
The visible.
Okay, visible. Somebody saying that's not visible. That's why.
Sir, it's visible, sir. So you are discussing this time this figure.
Okay.
That is why
Okay.
they are saying. Yeah.
Okay. Okay. So now try to understand the problems of structures such as stars. We have used the concepts of Rose equipotential. And what is the Rose equipotential? Basically, in Rose equipotential, we have to understand the whole system. This is a picture in front of you. This is the axis of this is a primary star. This is secondary stars, right? And these are M0, M1 are the masses of these two gas spheres. And M0 is much larger than M1. It is fact I have already discussed. D is the distance between two centers of the components. This is center of the primary, this is center of secondary stars, and D is the distance between these two, right? Suppose that the positions of the two components of this binary system is referred to a rectangular system of coordinate system having the origin, and the origins of the rectangular system exactly lies on the center of the primary stars, and this x-axis is joining the center of these two stars, right? This is x-axis and this is a y-axis, this is z-axis. I have missed here. This is a z-axis perpendicular to the x-axis here, and it is y-axis. And this whole system is revolving about the common center of mass, this D. So naturally, this line is perpendicular to the line joining between two centers of the stars. Whole thing is rotating and revolving, right? So basically, if this is so, then we choose a arbitrary point P, which is outside this, which is not inside the two stars, outside these two. P is an arbitrary point. We try to calculate what will be the potential at these points. So we calculate potential, and potential can be calculated by different ways. So total potential arises by many things. Many things means we have two components. So potential may be arises due to the gravitational gravity, like this, and potential may also arise due to the rotation. So rotational and gravitational potential can be calculated at any point P, and maybe apart from these two, maybe other factor also which can contribute in the case of potential, and we can. So presently we have confined our discussion to only gravitational and rotational. So I have written the equation. Psi is nothing. Psi is the total potential arises at an arbitrarily chosen point P outside the stars, not inside the primary and component and secondary component, right? I have written the actual equations of gravitational potential. Gm0 by R means what? That is P. So potential arises due to the primary component P, this primary component at point P. And what is this? This simple physics. Gm0. R is the distance between point P, from point P to center of mass M0, right? And R1 is the distance from point P to the secondary component M1. So we can calculate very easily the potential arises due to the primary component and secondary component. The first part is nothing. It is a potential due to the primary, and secondary is nothing. It is a potential due to the secondary component gm1 by r1. R1 is the distance here, and you will see I have not again. And but last part of this equation is nothing, half omega square is square. It is nothing. It is potential arises due to the centrifugal force. And because see what is this omega square? You know the centrifugal force is half of omega square is square. Omega is the angular velocity, and this is nothing distance. How to calculate distance? Basically, the coordinate is x. D is nothing here. It is so. If we draw perpendicular to this point here, it is nothing. This point will be here. This point will be x. This point will be x minus of d. This the coordinate of center is nothing. This coordinate will be here m1 comma d. I have not written here, but coordinate is m1 comma d upon m0 plus m1 and comma, because this is on like exactly on the x-axis. So the y and z component will be 0. Its coordinate here. This coordinate is m1d upon m0 plus m1 and comma 0 0. So that's why if we take the distance from this point to this point, that distance is nothing here. So half of omega square and distance square. This distance is nothing. I have taken here only. So basically we have computed total potential at the point arises due to these two components as well as centrifugal force. So this is the situation, right? And when this psi is nothing, it is a total potential. If total potential is supposed to be constant, this potential is equal to be constant. Psi is equal to constant. Then this represents surface, and this surface is known as Rose equipotential surface. Simply, you can say it is a psi is equal to be constant. It is nothing. It is an equipotential surface. But I have used the words Rose. Rose is nothing. Rose basically we have used generally Rose model with stars. Rose model stars is very much resembled with the real stars, realistic stars. Basically, what is Rose model? Rose model, I have considered primary component of the stars as the Rose model with stars. What is this Rose model? Rose model is, in this model, the entire mass of the star is assumed to be centrally condensed. That is, all the mass will be concentrated at the center only, and which is surrounded by an incandescent envelope in which density varies a square of the distance from its center. So that's why, since we have assumed m0 as a Rose model of a star, that's why the potential arises due to this Rose model is known as Rose equipotential surface. So this structure is a thing. From here we can calculate the Rose equipotential. That means a potential means total potential. And this is nothing. It is psi is a function of x, y, z. And you know in mathematics, if psi of x, y, z is equal to any constant, it is nothing. It is surface. And at that surface, everywhere potential remains same. So that's why it is called. First of all, it is equipotential surface. If you assume m0 as a Rose model, then it is known as Rose equipotential surface. So now we are going to approximate the structure of the stars by assuming at a Rose equipotential surface. Right now, this is a brief introduction about Rose equipotential. The question is, I have to use the concepts of Kipnahan and Thomas averaging techniques. What is this? You should also know this one. Basically, I already mentioned that is mathematically the analysis of the structures of the stars is not so easy, very difficult. And particularly when you introduce the concepts of differential rotation, our mathematical problem becomes very complex. And that's why always we study in the approximate way. Try to use some approximation. What type of approximation? Approximation comes in picture now using the concepts of Kipnahan and Thomas approach. So now from here, we have just completed and constructed total potential and also understand what is a Rose equipotential. If this is psi is equal to constant, that represents the surface, right? Now, here, this is averaging techniques of Kipnahan and Thomas. See, it is very, very interesting and useful. In order to study the effects of rotation and tidal distortions on the equilibrium structures of a gaseous sphere, Kipnahan and Thomas here in 1972 define a topologically equivalent spherical surfaces corresponding to the actual equipotential surface of rotationally and tidally distorted model. See, I have drawn a picture, two pictures. One picture is completely spherical in shape, and second picture is nothing, just look like elliptical size, distorted form of sphere looks like elliptical shape. So basically, this total potential represents this total potential, that is psi equal to constant, nothing is total potential, and this represents equivalent surface. So this is actual equivalent surface, and actual equivalent surface is nothing, surface of rotationally and tidally distorted gaseous sphere. What happened? Kepler and Thomas, what did some approximation here? What approximation? They have transformed everything on the topologically equivalent spheres. So everything on this actual thing happens on the right hand side, and same thing will happen on the right hand side, left hand side as a in approximate way. Suppose f and g are any quantities they define on the equivalent surface, this one right hand side structure, then the same thing we introduce on the right hand side, we have used the word f bar, g bar. F bar, g bar are nothing, they are the average values of the actual values f and g parameters defined on the right hand side structure, that is actual equipotential surface. So basically what is happening here, right hand side shape is actual equipotential surface, but left hand side is nothing, it is a topologically equivalent spherical surfaces. So now approximation comes in picture. Right hand side is actual, we have left hand side is approximation. The total approximation is done on the spherical surfaces only, right? So here Kepler defined f and g with the help of the quantity f and g. They have defined various other things, physical parameters like surface area, like gravitational force, average of gravitational force, other things. But one thing is preserved. I have used the word topological equivalent. Topological means something is common, other thing are the averages. So if f is defined on f is the actual value on the right hand side, f bar is corresponding average value on the left hand side topological spheres. G is a quantity on the right hand side structure, g bar is a corresponding average. But one thing is preserved. What is the volume inside this right hand side structure? And volume remains same of both the things. So volume of spherical body is nothing, you know, volume of sphere is 4 by 3 pi RQ. So basically what they did, one thing is preserved, one thing is common, that is the volume is same, other thing remains average in this concept, in this analysis. And that's why Kepler and Thomas used this analogical volume of the topological equivalent spheres like this. R psi is nothing, R psi is not the radius of the actual stars, R psi is the radius of topologically equivalent stars, and topologically equivalent stars nothing. Here we have the approximations of rotationally and tidally distorted stars, right? So basically approximation comes in picture, and since it is a sphere, and you know the value of a sphere is nothing, volume is v psi. V psi means volume enclosed within equipotential surface psi is equal to constant, right? But SI is nothing, SI is a surface area enclosed by the equipotential surface. You know the value of volumes in the sphere, that is 4 by 3 pi RQ, and it is understood. If you want to calculate surface S, it is also 4 pi R square. But we are not going to calculate 4 SI by this one. It is nothing. It is d psi is a surface element, taking the integral over the psi equal to constant d psi, a surface element. Is surface element taking the integral of our surface element. So this is not, I'm exactly writing 4 pi R square. I am writing here just like, so this is, I should write like this 4 pi R square for SI, but not so. Only one thing is preserved, that is volume, other thing remains average. So now I'm taking the average value of surface area, and average is calculated by this expression, like SI is equal to integral of d psi. D psi is surface element. And that's why I'm writing SI is not exactly equal to 4 pi R square. I have taken average here. So from here we have defined everything. F bar which is average of F defined as here 1 upon SI integral of F d sigma. So using these simple parameters, we have calculated G. G nothing. Now I cannot define G as Gm by R square in the general Newtonian mathematics, Newtonian mechanics. I have defined G as d psi by dn. What is d psi? D psi is nothing, it is equidistant surface. So it is a rate of change of equidistant surface with respect to n. N is nothing, outward normal. So just differentiate this one, take the gradient of these, we can find a value of G in different ways. It is not exactly Gm by R square, but later on we can write like this. And G bar. Now this is G, actual G, we can calculate, but in this case, the G bar means the average value of G bar within the equidistant surface cycle to constant. This can be calculated using this formula. This is all defined by the Copal. I have already used the words Copal, which started the work in 1970. I have used. So G bar, everything I have keep on defined, and you keep on the use results of Kippenhahn will be used by the Copal to determine the effects of rotation and tidal distortions, right? So this is the basic thing. Basically, physical parameters are volume, surface area of the spheres. Basically, our structure is original structure is structure is sphere, but due to the distortion, the sphericity is slightly disturbed, slightly deviate from the sphericity. So this deviation can be calculated by this parameter G bar, G bar inverse. It is the inverse of the gravitational force. Then SI, these all inverse value. Only thing is same here, volume. Volume will not be changed. Now, then Kippenhahn-Thomas defined these three parameters, U, V, W. Very interesting parameter. See, if you talk about this one, actual value of surface area, you know, for the spherical body, actual surface is not 4 pi R square. And but we are not getting this value. We are not using same 4 pi R square. We are taking R psi. So if really, if SI and 4 pi R square are different, then dividing approximate surface area by the actual surface area, we have some values different from 1. And different from 1 gives the idea of the distortion. If they U is equal to 1, then what will happen? U is equal to 1, then SI equal to 4 pi square. Then exactly we are getting the surface area of a sphere. But in general, it is not so. SI, U will be different from 1, exactly not 1. And so we can say these are the distortions parameter. Now, similarly, in the same way, you have defined V and W. What is V? We know if you calculate G, the value of G is nothing, Gm by R square, right? So it's the same thing. G bar is divided by Gm psi by R psi square. So it is nothing, ratio of the gravitational force. And it is a quantity. If this quantity exactly, B is exactly 1, that means we are talking about the spheres. But it is different from 1, we can say no, it is slightly disturbed value and there is slightly change. Different from 1 means we are not talking about a sphere, it is different from a sphere, right? So this, it is a ratio of two gravitational force, G bar divided by Gm psi by R psi square. Again, inverse of R psi, R square by Gm is the inverse of G, and similar G by inverse. So these are nothing, is actual distortions parameters. M psi is nothing, M psi is the mass enclosed within the equidistant surface cycle to constant, right? And these are the distortions parameters, U, V, W, right? We try to develop the equations of fundamental equations of stellar structures, and now in that we already define for the continuity equation, for the mass equation, for the temperature equation, luminosity equation, every equation. But in that equation, if these parameters U, V, W appears, that means that is not the actual equations of a spherical body. Now that is equations for rotationally and tidally distorted stars, right? So basically, next equation is Kippenhahn-Thomas now defined different way. Although if you go through the books of stellar structure, you can find the equation for equation for mass, then hydrostatic equation, temperature distribution, everything will find. But with the help of distortion parameters, U, V, W, they have again defined FP, FT and introduced in the equations of this is a equation. How mass varies with respect to time. It is a continuity equation. And also you can say height. So these all are well-known equation, stellar structure equation, but in terms of the Kipnahan-Thomas distortion parameter. RTD means I have used RTD means rotationally and tidally distorted model. So this is actual equations of rotationally and tidally distorted. But interestingly, if all U, V, W all becomes one, this given equation exactly reduces to the equation of the spherical gaseous sphere. Spherical gaseous stars, right? So basically, this is the original equation which consists of the certain distortions parameter. Now in the distortions, we have presently considered only rotational as well as tidal parameters. Now people are also working in this field. We're not only talking about rotational and tidal, they are also considering different influences like magnetic field, like Coriolis force, other force also. But presently I have confined my discussion to these two only. So these UVW can be created in different way also, but it is only for here for rotational and tidal. Now, once you have the equation, then a stellar structure equation has this equation has some boundary condition because this is a well-known equation. So R size is nothing. R size is the radius of topologically equivalent sphere. When R size is 0 at center, then mass is also 0. M size represent mass within the equivalential surface cycle to constant. Here L is nothing. L represent because star has own energy, own luminosity, right? So here L represents luminosity, that's brightness. You know, there's difference between stars and planets. Stars generate your own energy, and therefore there is a brightness in the star. But planet doesn't generate any energy. Planet is illuminated by the light of the stars and sun like that. Basically, here L represents luminosity within this equivalential surface cycle constant. So now naturally it is center is 0. Both mass and luminosity will be 0 at the center, but at surface, what will happen? We go from center to surface, outer part, then R side, radius will be the complete radius. Here, capital R represents whole radius of the topologically equivalent spheres, total mass, total radius. And M0 is nothing, total mass of the equivalential surface. Right, and same way at the surface, this is a P represent pressure at the surface. T represent temperature enclosed within the equivalential surface cycle constant, and L. So this is a parameter and known as a boundary condition. Now, so we have, and I have already mentioned that when all U, B, W, these are parameters. Naturally, FP are based on, in this previous case, FP are based on UVW. If all three parameters UVW, FP are 1, then what is happening? We are getting the actual equation, fundamental equations of stellar structure, and with the same boundary condition where we have original equations can be found where there is no distortion, right? So due to distortions, we have terms UVW and FP. So what we will discuss in further analysis, we have always these terms AU, V, W, FP, different types of equation that represents we are introducing some distortion in the structures, right? So this is a basic thing. These are basic things. Now with the help of this one, our Professor Mohan and Saxena have also developed new equation of stellar structures. I'll skipping that part, but I have just overview. I've given overview about what is this distortion, how it comes in this actual equations of stellar structure and like that. Now come to this one, differential rotation. I have already mentioned some of the stars are not rotating uniformly, that is solid body rotation. Stars are also rotating differentially. I have mentioned what is differential rotation. Differential rotation is nothing. It is basically a star is a gaseous body, and in this case, fluid particles is moving about the axis of rotation. So in this case, each fluid particles having different angular velocity. Angular velocity changes point to point in the inside the stars, and that's why you say a star is rotating differentially. One of the examples of differential rotation, a differential rotating star is Sun. There might be many more. Our latest situation is Sun. So naturally, I will also confine our discussion to Sun applications of our model to Sun. How our model is realistic, how model is very relevant, how we can apply this theoretical model to any realistic stars. So basically, I have considered here differential rotation. So when I would say differentially rotating stars, then a star must assume certain type of differential rotation law. What type of law? I have already mentioned in the previous analysis when uniform velocity means constant. Each particle has same angular velocity throughout in the stars. No particle has different angular velocity. But when you say differential rotation and angular velocity changes point to point, that means we have to consider angular velocity as a, some functions of distance of parameters, right? And that's why we have assumed a law. That law is symmetric about the axis of rotation, right? That's why I have taken omega is nothing. Omega is the angular velocity. Omega depends on s squared, not s. S is a distance of the particle, this particle from the axis of rotation. Due to the symmetry, I have taken omega is a function of s squared, right? So I have assumed, I have proposed this type of differential rotation law, and if you assume omega squared, then mathematically use Taylor's expansion, use Taylor's expansions of this one, and retain some terms up to second order smallness in s squared. We have our generally, since we have assumed the symmetry, that's why I have taken omega squared. Omega square is nothing. It should be basically omega square equal to omega square is a squared function. So basically, this b is 0 plus b1 is square plus b2 is 4 is nothing. It is sort of the Taylor series expansion of the function up to second order terms in the smallness b in the b0, b1, b2. I have only taken. I can take more term also, but since rotation is small, that's why higher powers of this one will be very negligible. That's why I have not considered. I have taken only second order smallness in this one. So all here b0, b1, b2 are constant, and s is nothing. Since this is a particle point, this is distance, and this is angle theta. What is this? We can obviously say s is nothing. S is equal to r sin theta. So basically, we can say we can calculate s distance like this. But see, if you these b0, b1, b2 are constants, changing by putting the different values of b0, b1, b2, what happened? What happened?
Screen is not visible, sir. Now, आ गए. Yes.
Okay. Okay. So just a minute.
So we can can we take break, sir, for 5 minutes, sir? Can we take?
We can do. No problem. If you have, I have my. If you have any doubts, any question in your mind, you can ask me. You can stop me for the discussion. No problem. So if you have any doubt, any question in any, you can ask in the gap period. We have gap. We have time for 5 minutes for discussion.
Yeah.
So if you have any questions in your mind, yes. ठीक है वही कर रहा था ठीक Am I audible?
Yes, sir. Yes, sir. You're
May I
audible.
start? May I start?
Yes, sir. You can start, sir.
So I was talking about differential rotation in the stars. Recently here I have taken a single star which is rotating differentially. And that's why we have assumed this law of differential rotation. And it is supposed to be a Taylor's expansions of this function, omega is equal to omega square. And therefore, to make it symmetry of the angular velocity about the axis of rotation, I have taken omega square equal to b0 plus b1 square. So now here all b0, b1, b2 are constants. By taking different values of b0, b1, b2, we can generate a variety of differential rotation inside this. Sometimes you see the angular velocity start to increase from center and decrease at the surface, and sometimes started the increasing stage from center and decreases at the surface. Not only one, there are different. I have done a lot of experiment for this one. Different types of laws we have generated, and using different types of law we have studied their structure and further analysis. So basically, we using the parameter b0, b1, we can say these b0, b1, b2 are also the rotational parameters, and they are all in the units of the angular velocity units. So we again, when s, this is a function s equal to r sin theta, how it comes, it is understood, simple understood. See from the picture, is any part here, and this distance is s naturally, and this s is varying point to point, right? That's why s equal to r sin theta. So theta equal to 0 is what? If theta angle is 0, then we are along this perpendicular distance y, and this y axis is nothing. It is nothing. It is a polar side. We can say it is a pole of this stars. And when theta equal to 90 degree, that means what? It is along the x-axis. It becomes a equator. So x-axis represents the equator. Y-axis represents the pole of this differentially rotating star. Now what happens? Now in this case, if we assume the law, if s equal to theta equal to 0, then s will be what? S will be sin 0, 0, s0. So now omega square exactly will be b0. So I have written WP. WP means nothing. It is a polar angular velocity. Angular velocity along the pole, right? So it is nothing. According to the formula, it should be exactly a square root of b0. Now when theta becomes 90 degree, then what will happen? The x is nothing. S is exactly r. And using this, we are again along the equator. So I have used capital R E. RE represents equatorial radius, and that's why omega E represents equatorial angle. Basically, I want to show you that in the stars, equatorial part rotates much faster than the polar parts, and it is everywhere inside this star. So that's why we pole or equal the equator. You can go in different directions also. It depends on the how we have chosen, we have proposed, and a variety of angular velocity can be generated by choosing different values of b0, b1, b2. Right? We have traced the graph of this one, different types of laws we have proposed. Due to time constant, it is not possible to draw all those graphs, but we have done in our analysis. Anybody who is interested, they can see this work in my this is available on the net. You can see. Now, the question is, I have already mentioned. Now we have assumed a single rotating star rotating with differential rotation. Now need to use some approximation. Now approximation is same, Rossi potential, but not for the previous. In the previous, we have considered binary stars. Now I'm considering single star. So in this single star, how to calculate total potential at any point. Now see these single stars, we have only one part. Potential arises two things, you have the gravitation as well as due to the rotation. So gravitation is what? Here change in angular velocity equal to change in potential equal to half of omega square d square is angular frictional force, and dv is nothing. This is due to the gravitational force. So it is obvious v equal to gm by r. So basically, using this law and this use, again find the new type of total potential in the single rotating star rotating with differential rotation. Now I have not written here. So using this omega square here, right? B here, and now put s equal to x square y square, the distance. Then basically, and using this law, we have written completely omega, and writing omega in the non-dimensional form. I am writing it is not dimensional form. Earlier I have used psi in the dimensional form. I have used this r lambda nu using this concept. I have changed x equal to r lambda, y equal to r mu, z equal to r nu. So using this non-dimensional parameter, we have written total potential in the non-dimensional form, and this is a total potential in the non-dimensional form. We can say rho equipotential. Now earlier rho equipotential in the dimensional form. Now it is rho equipotential in non-dimensional form. Now with the help of psi, we can do many things. As I discussed previously, with the help of psi, we can construct radius. We can construct volume, surface, gravitational force, inverse of gravitational force, as discussed by the Kipnahan Thomas. Right now, I'm using this psi. So every time our analysis depends on psi. Surface is nothing. Equipotential surface. Using equipotential surface, we are trying to approximate the shape of the rotationally and tidally distorted star. So basically, now using this we have the relationship r theta phi as discussed by the Kopal. We have used the total potential psi, and r is relation is obtained r theta phi. That means we can have interesting study on this application also, because we have to, whenever we have to analyze this application. Sorry, we have to analyze distance in effectively. Then you can see it is nothing. Everything we can calculate r with the help of psi, and with the help of psi, basically psi is inversely proportional to r. R increases, psi decreases, I increases. So basically, with the help of this one, we can construct a polynomial in terms of r, and using this r, we can also find the value, what type of equipotential surface we are using. Basically, that using this, we can also study the Rosset limit. That is part of the binary system. It is not here in the binary system. So very interesting. We have, using this, we got the relationship between r theta phi. Basically, here theta is nothing. Here theta, how theta comes? Because nu is equal to, I have already mentioned, nu is nothing, it is cos theta. So using this, we got r theta phi, and whenever it is required, you can do. And same r is used to calculate the gravitational force, the volume, surface area, like this. And I have calculated this using Kopal's results and movement sectional approach. Explicit form of volume, surface area, not exactly in the explicit form, but it is in the series form, infinite series form. And I have discussed and also studied this infinite series. Nothing, it is convergent series, exactly convergent. So sometimes we have raised, some people raise the questions, why using the infinite series? Sometimes it may be convergent, may not be convergent, but we have studied and got a converging situation. So basically, this is situation. Now, what is this? V psi is nothing, volume enclosed within the equipotential surface psi equal to constant. It is a volume. And now our volume of the given stars is distorted stars is like this. If all B0, it is in terms of distortion parameter B0, B1, B2. Now just assume it is what? 4 by 3 pi RQ. So this is the radius distance. It is completely 4 by 3 pi RQ. So all terms are here 0 except one, that is B0, B1, B2 are 0. This completely reduces to the volume of sphere. But due to the terms B0, B1, B2, we have some terms different from the sphere, and this gives the distortions in the volume. So right now, by different values of B0, B1, B2, calculate volume. Similarly, we have computed the expression for surface area. We have computed the expression for G bar. We have computed expression for G bar inverse. I have not. I have shown only you only the volume enclosed within surface. Now, once you know all three, four physical parameters like volume, area, gravitational force, then in the stellar structure equation, as discussed by the Kipna, Han, and Thomas, again I have discussed we have constructed new equilibrium structure for differentially rotating stars, and this equation, as discussed earlier, a same equation, but in terms of the distortion parameter arises due to differential rotation law. It is a dm psi, but in terms of dr0. R0 is nothing. R0 is here this is a parameter defined in terms of 1 upon psi. And mass equation, hydrostatic equation, luminosity equation, temperature distribution equation, everything we have learned here. And these F1, F2, F3 again are the parameters, distortion parameter. If they are one, naturally they reduces to the original equations of spherical structures, right? So I have introduced the distortion due to these terms F1, F2, F3, and these all F1, F2, F3 are calculated with the help of R psi, right? So basically, this is nothing. Now, new expression for distortion parameter for the differentially rotating stars, right? And now, once you know these stars, our job has been done. We have developed theoretical model of differentially rotating stars. Now, this can be applied to any realistic stars. We have the equation for the realistic star. If go through the books of stellar structure, we can white dwarf equation, topic model for stars. You know, we can also apply the same thing on the white dwarf stars. And the interesting point is white dwarf is very popular in the sense that our Chandrasekhar Subramaniam got the Nobel Prize on this principle. You must be knowing Chandrasekhar mass limit. M mass is 1.47 solar mass. And if this is the mass, then the end of that star will be in the form of white dwarf stars. This is evolutions of stars. So we can now we are ready to apply this equation to any realistic star. I have chosen here a polytropic model of stars. It is very, very useful. That in this stars, pressure and density are related. We have some laws by which there is a pressure distribution law, there is a density distribution law for particular polytropic models. And using this, it is a part of, in fact, thermodynamics. I'm not using that part in details, but using this polytrop, we can study different types of realistic stars. And see, I'm going to the next job is here. This I have chosen polytropic model of stars to describe the inner structure of any realistic stars. So our topologically equivalent spherical model is supposed to be rotationally distorted stars and behaves as like a polytropic model of star. And if you say it is a polytropic model, then in the polytropic model, pressure and distribution follows this type of distribution. It is P psi means pressure enclosed within the potential surface psi equal to constant, and that is not equal to Pc psi equal into theta psi into to the power n plus 1. That means Pc psi is nothing. It is a central pressure within the potential surface psi, and P psi is nothing. It is any potential at any point within the potential surface. And theta psi nothing. Theta is a variable varying from center to surface, and generally it is a parameter by which we decide. And n is nothing. Capital N is a polytropic index. It is very, very important because mathematically Chandrasekhar has done a lot of work on this polytropic model, and they have shown mathematically that n cannot be larger than 5. N varying from 0 to 5 only. If n greater than 5, then there is no realistic star. Radius becomes infinity. There is no existence of realistic star. This is very beautiful analysis on this polytropic model. Same way we have discussed. This is the density distribution. Rho psi, density within the equidistant surface cycle constant, equal to rho c psi, central density within the psi. Theta psi is a parameter. Again, theta psi is a variable varying from center to surface. In this here, right? And using this pressure and density and taking the help of the previous equation, we have again developed the new equations, and that equation is known as polytropic model of stars known as Lane-Imden equation. Nowadays, it is a very popular equation known as Lane-Imden. This equation is nothing differential equation, non-linear second-order differential equation, and this equation, if we talk about the Chandrasekhar has for you for the Lane-Imden equation, and Lane-Imden equation is nothing here. N is a parameter. It is a polytropic index. I have already mentioned. And nowadays, mathematicians are solving this equation. They are not even finding the exact solutions of the differential equation. Presently, exact solution is obtained for n equal to 0, n equal to 1, n equal to 5. And for other 1, 2, 3, 4 like that, we can try to find this. So to try to solve this non-linear differential equation numerically, we can find the solutions of this equation numerically. And see, n is a very interesting parameter. This is called polytropic index, and polytropic index n is 3. It represents a standard model of stars. Our sun is also a standard model of star, and the polytropic index for sun is 3.75. N equal to 1, it is convective model of star. N equal to 5, we have a highly centrally condensed star. But whenever n goes to n is greater than 5, that means our R0 that represents the radius of the star, it becomes infinity. It is shown mathematically. If we go through the books of Chandrasekhar's interstellar structure, you can find the analysis, very interesting analysis. But nowadays, mathematicians are also solving this Lane-Imden equation for other parameters, which is not solved so far analytically, like 2, 3, 4, like that, right? So this is the basic equation which represents the equilibrium structures of rotationally differentially rotating polytropic model star. Now we solve this equation using numerical techniques, and I have used this. This equation has some condition also, and that condition here we have parameters A0 and B0. Naturally, it is a parameter which consists of some distortion parameter B0, B1, B2. It also consists of B0. We all are 0. Then it becomes nothing. It is simply original Lane-Imden equation, right? So using A and B, we are going to introduce some distortions parameter arises due to the differential rotation. Now this is the A0, B0 expression in terms of infinite series, right? And here, if R0 is 0, it is a boundary condition. At the center, theta psi, which we assume the parameter variable parameter. So theta psi becomes 1, and derivative of d theta psi with d R0 is 0 in the center, at the center. So basically, this is so, and when surface, we got a surface that is R0 is equal to R0s, theta psi becomes 0. This is the condition by which we try to find a solution of this non-linear differential equation in the numerical form. And presently, we have used here the Runge-Kutta fourth order method to solve this equation. We have started, since there is singularity at the center, there is a singularity at the center. You see, this is here R0. R0 comes here 1 upon R0 square, like that. So naturally, this differential equation has singularity at center R0, and to start the numerical process, we have using series solution, we have solved this differential equation numerically using Runge-Kutta fourth order method, and we got solution. Initially, Chandrasekhar also got a solution. We can find different values of n. We have different solutions. How n, what theta, why our solution varies with respect to different values of n. N0, we have different solutions. This gives the distributions of pressure and density within the stars. Star. Different n, we can construct different realistic stars. What I already mentioned, for n equal to 1, n equal to 3.75, we have got the model of sun also, which is also differentially rotating, right? So this is our model. This is our mathematical model for differentially rotating stars, right? And now I have tried to apply this model to the sun so that some of the results available for sun can be matched, can be verified, can be compared also, right? So this is situation. This is our differentially rotating model of the stars. Now, after this, I have not shown you the results for different n. What is n equal to 1? What is the results for how theta varies? What is results for theta varies for n 3, 4, 5 like that? I have not done. I have skipped that part. I have tried to use this concept in the application, right? And therefore, I have chosen a new law. There are certain differentially rotating model of sun. People have done a lot of works on this differentially rotating sun. One of the author is Clement, right? Here says solar equatorial surface is rotating more rapidly than surface near the poles. See, poles and surface. That's why I have computed and given the formula for both. What is a polar angular velocity? What is equatorial angular velocity? And this is a fact. Equatorial surface is rotating much faster than polar surface. So that's why this is a fact. And Clement also shown this thing. So Clement have introduced a new law of differential rotation like this. Omega theta. This is a law of differential rotation proposed by Clement in 1970. And using this, they have computed the periods of periods near center of the sun, and they got like this. The rotation period near the pole they have computed 32 days per cycle, one cycle in 32 days, and period near center is 1.8. So now can you just imagine how is what type of variation here is in the angular in the period of rotation. This is the results obtained by Clement. I have tried to match our result with Clement also, right? There is also one author, Clement. Clement has also proposed new law of differential rotation like this, omega square. Some of the authors like Sunil and Sima, they have also used this type of differential rotation. And here, this is a thing, you have the same thing, exactly same thing. This is also matching our results. It is here, I varies from ratio, I varies from 1 to 3, AIE minus BI. So if you put here, then it is nothing. A1 e to the power minus B1 is a square plus A2. Our is simply B0 plus B1 is square, B1 into B1 into S square plus B2 into S to the power 4. Exactly, we can compare this differential rotation with our role computation, and using this, we can also compute the parameters, structure parameter for the sun. And we have done this analysis, and I've seen I'm escaping many things because due to time constraint it is not possible. So we have different models. So our B0, B1, B2 are written in terms of the model proposed by Clement and some other authors. That's why I have taken 1, 2, 3. And there was also Gironis in 1981 who has also developed the model of sun, right? So basically, model 1, model 2, model, these are our model, and this is results obtained by journeys and different structure parameter of sun we have computed like this. Polar radius RP. It is this is our model 1, this value. Model 2, model 3, and Kipna and Juris also same thing, and they got the values of the polar radius like this, 6 points like this. Our result is very close to the exactness, and so this justify, and it is not only this one, we can find for every parameters, polar radius, equatorial radius, right, and volume of the sun, surface area of the sun, oblateness means how oblateness basically. Due to rotation, our structure will be oblated near the poles. So oblateness near the poles, it just doesn't look like exactly sphere. There is oblateness. So this is a sigma parameter is computed, and it gives the distortion is not exactly same. And same thing, what Juris computed, our result is very much resemble the same, not exactly, but very close to that one. This central angular velocity and polar. See, what happening here? We have chosen the rotation law that has some drawbacks, and I'll discuss drawback. See, what is the same? What is period at the center here is 31.99, and period at pole is same thing. Both are same. Both time. This is the main drawback. But here Jonas computed this reason, but Jonas has not computed the here the polar period at pole. This is the drawback in our assumptions on the differential rotation law. I will discuss later on. And period near equator is 25. So 25 is much larger than pole. So this is the result, and we can say this variations gives the actual variations in the sun also resemble some of the results not exactly matching, but most of the results are matching with the exactness. So this way we have first of all developed the mathematical model of differentially rotating stars and then applied to the actual rotating stars of sun, and we got the result. So result is, since we have our approximation, our result is in approximate way, we cannot say with guarantee that the result is very exact. There must be some error. There must be error is appreciable, it is acceptable. So this is analysis. This type of way we can, although it is a part of astrophysics, but completely transformed into the mathematical problem. And mathematically we have shown that how this method, how this model is realistic, is valid, acceptable, right? See, what I'm talking about regarding the polar velocity and equatorial polar velocity, sorry, central velocity 31 point is, and period at pole. Center and pole both are same. Why? The reason behind this is you have to think, you can go back to the law of distribution. When you talk about this law, I have mentioned, this is supposed B0 plus B square plus B. So this O is nothing, O is center, and this portion here is nothing. So we move along y-axis, you are moving along the pole, right? So what is the angular velocity here? 0. Same angular velocity remains same near this y-axis, and that's why polar angular velocity and central angular velocity remain same. This is the main drawback I have not considered at all. That's why there is a need to modify this law of differential rotation. This depends on S only. That is, S is nothing. S is the distance of the particle from the axis of rotation. But I have not considered this particle from the equator also. And if you consider this part also, the depth of the distance of point P, this point P from the equator also, then actual differential rotation can be considered. Therefore, this is a lemma, and that's why we cannot say actual angular velocity at center is what, actual angular velocity at pole is what. They, in this case, both will be same, obviously. But if you introduce a new concept, then this should be functions of Z also, that is variations along Z axis also. That is this distance, suppose Z is also, Z parameter is also considered here. That if omega is supposed to be functions of two parameter, S square and Z square, then actual situation comes in picture. Then you can find all type of variations at any point, near equator, near center, near pole. Every time law will be changed, period will be changed, right? So there is some drawback in this case. I have also modified this law and studied, a lot of studies had done. So time constraint is not possible. If you have interest in this part, you can go through my paper available on the website. So this is all about the differentially rotating models of stars, and finally we have applied this case to the sun also. This is all about our study. This is a very short presentation, and with time we'll get, I'll discuss many more things about rotation. If you have anything in your mind, any question, you can ask. So I have finished my lecture.
से पूछा बदलाव, चौथे से पूछा बदलाव, उन्होंने कहा बदलाव का मतलब बोले केजरीवाल. तो एंकर
Yes, participant have any queries can ask to sir.
Yes, you can ask. Any participants has any queries, they can ask.
Tarun sir, Tarun is there, sir. Yeah.
Hello, sir.
Hello, Tarun.
Sir, I have one question.
Yes.
So, what is the meaning of differential rotating stars?
I have already mentioned, differential rotating stars means since star is supposed to be a gaseous field, different type of gases is there. I have already mentioned that when we talk about this one, then it is gaseous sort of fluid also. So in this inside the stars, the fluid particle has a velocity that is called angular velocity. Angular velocity of each particle is varying point to point from the axis of rotation. And this is in some of the stars it is found, and that star is a differential rotation. Okay. There are some solid body stars. There's any particle inside the stars has the same velocity, constant velocity, and that is called solid body rotation. So this is not the new thing; it's very old concept. Even our example, sun is also rotating differentially, right? Okay. So there are many stars, not only this, many stars rotating differentially, and many people are working on the differential rotating stars.
Okay, got it. Thank you, sir.
Okay.
I have one question, sir.
Okay.
Yes, sir, what will happen when we are taking axis of that in binary system of stars, we are taking that axis of rotation is perpendicular, but if we are not taking it is perpendicular and it is inclined at some angle,
yes.
then
Yes.
what will be the differences in the structure parameters, sir?
Yes. Basically, presently our study is completely confined that axis of rotation is perpendicular to the plane, XY plane. But and that's why I have computed everything. I have computed using this concept, computed potential, total potential, then Rossi potential surface, and using Rossi potential surface, we have actually approximated the structure of the stars, right? But whenever we treat the angular axis of rotation is not perpendicular, inclined, then everything will change. Now in the new way, we have to create potential, total potential, and Rossi potential surface. In this case also, only thing we have to change the equations for total potential. But whole thing, if potential equation, this will be not be same. We have to change. And some parameter we added in this equation, and then we have you know there is author Avni. Avni has done this type of work also. We consider inclined axis, and when he got the potential equation, then potential equation is equal to be constant. It becomes Rossi potential. Whole analysis will be changed. Right? We can do. There are a lot of done on this problem where axis of rotation is not perpendicular; they have inclined by certain angle.
Means, sir, we can also calculate.
Gopal has done this type of work also.
Okay. Means, sir, we can also calculate eigenvalues also.
Yes. Because basically our main aim is to generate the potential function. Once we have potential function and using potential function and take the help of the Kipner and Thomas average approach, you got the UVW. And whenever UVW terms, distortion parameter terms appear in any equation, whether the structure equation with a boundary eigenvalue, boundary value problem equation, then distortions effects appears. It will magnify the results, right?
Okay, sir.
And now not only we have seen nowadays people are introduced changing the size. Only our analysis is use the approximation in most accurate way. It is not possible to say result will be exact because everything is approximation. I've seen our volume remains same. Otherwise, everything is approximation. We can change. Sometimes we can change the concept of Kipnahan Thomas also. Okay. The people like I have missed the name. One of the authors have changed the concept. We have different approach also, but this approach, whenever you construct UVW, it all depends on size. Psi equal to what? Total potential. And in this case, lot of parameters can be added. Not only the gravitational and rotational. You have seen in our some of my students have introduced the concepts of Coriolis force. I have done my work also where I have also introduced the effects of magnetic field.
Okay.
Although there is a magnetic two bodies here, binary stars, secondary is revolving about the primary component. So naturally through components there must be some gravitational field, and gravitational field also affects the potential. We have also introduced a new form of potential has been develop, that is modified Rosset potential. Not apart from this. This is avoiding your two-body problem. Only we have primary component and secondary component. Same idea can be extended to trinary star also, multiple star also, right? So
Okay.
there is a lot of scopes to do more work in this field.
Means that we can take triple, matlab, instead of binary.
Yes,
we can take
we have
binary.
concentrate our work on two-body problem only. Binary
Yeah,
stars means we can say roughly restricted two-body problem.
two problems. Matlab, multiple stars we can take,
You
sir.
can, somebody has extended in different ways, not using our approach, different ways, but we can do also.
Okay,
We can do
that's
also.
good, sir. It will be new approach, sir.
New approach, new approach.
Okay,
See,
sir.
and you know our work is basically start from the Gopal's works and Kipnahan Thomas approach. Now these two, merging these two approaches, we are developing our new thing and other thing. But here Gopal has already introduced. Don't go for the Rosset. Go for some other approach also. So far we have not done so far. There is a Rosset approximation, Rosset coordinate approach, and our analysis is this. But Gopal also suggested use Clade's coordinate form.
Yeah.
Using Clade's coordinate form, new type of structures can be studied, right?
Okay,
So we are those who are interested and very courageous to do more work in this astrophysics, they can do. A lot of mathematics are involved and mathematicians are required. Sometimes mathematicians apprehend, oh, you are studying the astrophysics. Astrophysics is a part of physics. Although it is a part of physics, but it is completely applied mathematics.
Yes. Okay, sir.
Okay, thank you so much, sir. So anyone has any query? Another one?
I want to say something. I have one thing. Due to time constraints, I have not discussed many things about this. Many mathematical aspects I have missed. But those who have interest in this part, they can see the works of Dr. Seema Seni, Dr. Sunil Kumar, myself, Dr. Chandra Mohan, Dr. VP Singh. They have all done this problem, and we have a lot of publication available in the on the website. They can do and study, right? Many things I have missed. It is not possible to discuss all the things here. So those who have interest, they can contact me also. I'll discuss, and they can study my work also. Okay, thank you.
Okay, thank you, sir. But you are giving a very interesting talk and informative also. So we would like say to thank again to our speaker,
Yes.
Professor Arvind Kumar Lal ji, and that is thank you. Anyone has any query, so please can ask. Otherwise, we will end this session. Okay, so now this time and this day, our online sessions are completed now. 6 days are completed for online
somebody
sessions.
just asked, excuse me, ma'am, somebody raised a hand, I think T.
No, that is Tarun sir already asked the question.
Ask question. If any more things she asked?
No one, I think so.
Nothing, I am seeing somebody raising hands.
Actually, yeah, Tarun is there, but already he asked the questions.
Okay, no problem.
Okay, so now from Monday we have started the offline sessions. So that is the inauguration on the Monday, 7th November. So all of you participants, all of you are invited for the inauguration and you have to come. And that is the first day of the offline sessions. So please come at the time. Your inauguration will be start at 9 a.m. and first you have the lecture. First we have the inauguration session. After that we have the lecture, one lecture, and then we have the lunch. And after lunch we have one visit that is from the in DRDO lab. So all of you please come on the inauguration and attend your FDP at 9 a.m. on 7th November.
May I leave?